What if alien life actually looked like this? On April 17, 2025, NASA announced something truly significant. They officially reported detecting the most compelling evidence yet for signs of life beyond Earth. The target was K2-18b, an exoplanet located 124 light-years away. The key wasn't about seeing a specific creature, but about detecting certain chemical compounds in its atmosphere. Here on Earth, these molecules are almost exclusively linked to biological activity. What's more, the concentration of these molecules was about 1,000 times higher than on Earth. This means that if these signals truly come from biological processes, that planet might not just harbor life, but could support a remarkable diversity of it. This pushes the question to an even more thrilling level. If life does exist there, what would it look like? NASA isn't just making wild guesses. They're using the established rules of chemistry, physics, and biology as their foundation to tackle a practical question. If you drop life into various extreme, non-Earth environments, and it has to survive, what forms would evolution force it into? Let's follow this line of reasoning and see just how bizarre these theorized life forms could become. Some might be as massive as Mount Everest. Some predators could be more terrifying than prehistoric dinosaurs. And some forms might be so strange you'd question whether they're even alive. First, let's zoom out and not fixate on a single planet. The Milky Way alone may contain over 100 billion planets, each one different. Looking further out, the estimated number of galaxies in the universe is between 100 billion and 2 trillion. It's genuinely hard to wrap your mind around that scale, but precisely because the numbers are so astronomically large, it becomes difficult to believe that among all those worlds, there wouldn't be at least a few places where life could emerge and thrive. Yet, the reality is a tough pill to swallow. To this day, we haven't obtained a single piece of direct evidence proving the existence of extraterrestrial life. Forget complex life. We haven't even found the simplest microbe. However, that doesn't mean it isn't out there. On the contrary, a growing number of scientists lean toward a different assessment. Discovery is only a matter of time, and it might happen sooner rather than later. But that most pointed question still lingers. If life truly exists elsewhere, what would it be like? Right now, NASA is advancing a project called HWO, the Habitable Worlds Observatory. It's a next-generation space telescope with a clear mission. First, find at least 25 potentially habitable exoplanets, then analyze them for signs of life. The mission is scheduled for launch in the early 2040s. But you might ask, why wait so long? Why wait so long? Can't we take a step forward now? We can actually run a simulation first, based on existing data, hypotheses, and observations. Astrobiologists are already trying to imagine how life beyond Earth might develop, what evolutionary paths it might take, what rules it might follow, and how different it could be from life on Earth. On Earth, the foundation of life is water. Roughly 4 billion years ago, the first cells and simple life forms emerged in the oceans. So, following that logic, the first type of potentially habitable world we should consider is a true water world. Welcome to TOI 1452b. It's about 100 light-years from Earth, with a volume about 1.5 times that of Earth, and a mass nearly 5 times greater. But the most mind-boggling aspect isn't its size, it's the water. Scientists estimate that about 30% of its mass could be liquid water. In other words, it might hold roughly 7,000 times more water than Earth. This suggests it could be a complete ocean planet, entirely shrouded by a global sea, with the potential to nurture incredibly rich life. But a question immediately arises. Would the creatures in TOI 1452b's ocean look similar to Earth's marine life? To answer that, we need to grasp a concept called convergent evolution. It's simple. If environmental pressures are similar enough, even if life starts from completely different origins, it can evolve to look remarkably alike. Consider fish, dolphins, and ancient marine reptiles. Their ancestors were entirely different, but they all make their living in water. As a result, their bodies evolved toward the same shape, streamlined. That's because this form allows for faster, more energy-efficient movement in water. So, looking back at TOI 1452b in its oceans, especially among creatures that need to swim constantly, might they also evolve long, streamlined bodies? That's a reasonable inference, not pure speculation. But this rule might not hold when it comes to truly gigantic organisms. Once size reaches a certain extreme, speed isn't necessarily the top priority. Furthermore, even if TOI 1452b's gravity is somewhat stronger than Earth's, in water, it's less noticeable. Buoyancy counteracts much of that burden. Consequently, life might more easily evolve to exaggerated sizes. Imagine that on that planet, there could be creatures 200 to 300 feet long, about 60 to 90 meters, 2 to 3 times larger than a blue whale. Their bodies might be shaped like torpedoes, longer and smoother overall, with more complex internal structures. They might have a huge, sail-like dorsal fin on their back. It might look like a shark's fin, but its purpose could be completely different from steering. It might function more like a biological antenna, or a light-sensing organ, capable of emitting intense pulses of light. Thus, their method of communication might not rely on sound, but on flashes of light, a flickering code, potentially developing into a whole language of light. But an urgent question immediately follows. Where would the energy to sustain such massive bodies come from? Eating alone might not be enough to support them. So, what then? One more radical speculation is, their skin might evolve into a specialized system that captures light from their parent star, converting light energy into bioelectricity. This would provide an additional energy channel to power their muscles and nervous system. As a result, they wouldn't need to constantly hunt to move and survive. If that were the case, then Earth's largest animal, the blue whale, might only be considered medium-sized in that ocean. Of course, it's important to remember one thing. These are still scientific hypotheses. They are deductions made by astrobiologists based on physical laws, cross-referenced with the physiological mechanisms of Earth's deep-sea life. Whether they actually exist, or if anything even remotely similar is truly out there, can only be answered by time and future observations. The truly bizarre parts might not be near the surface. The deeper you go in the ocean, the farther from light, the more alien life could become. In such an immense water world, ecosystems would likely be stratified by depth. For every mile you descend, the environment becomes more brutal. Pressure increases, light can't penetrate, pressure mounts, light fades away, and life forms begin to look more and more extraterrestrial, unlike anything familiar to us. Earth already provides us with a reference point. Even in the extreme environment of the Mariana Trench, 7 miles deep, creatures like amphipods and sea cucumbers manage to survive. They withstand pressures equivalent to about 1,100 atmospheres. But TOI 1452b's ocean volume could be 7,000 times that of Earth's, with depths possibly reaching dozens of miles. Pressures at the very bottom could even exceed 8,000 atmospheres. Imagine, even the most robust deep-sea submersible would be instantly crushed flat under such pressure, flattened like a thin sheet of metal. Therefore, if life truly exists at such depths, it must have circumvented the hard limits of our understanding. To survive under such terrifying pressure, body structures would need a complete redesign. They might have almost no internal cavities, instead being filled with high-density fluid or elastic tissue to resist compression. Hard structures like bones or shells would become weaknesses, as under such pressure, they'd likely shatter. Thus, a more plausible image is that these organisms would likely have soft, gelatinous bodies, able to deform with pressure without breaking. Descending further, darkness becomes an absolute rule. Where there is no light at all, eyes become useless. They might evolve more sensitive receptors to detect vibrations, chemical signals, or electromagnetic pulses. Anything that allows them to navigate in absolute darkness. Some might even produce their own light, because in that world, light isn't scenery, it's a tool. Like Earth's anglerfish, they might rise to shallower depths, using light to lure prey that can still see. Then, at the perfect moment, strike from the darkness. So, TOI 1452b represents a potentially habitable world like this, an endless ocean, with biodiversity stretched to unimaginable extremes. But the questions don't end here. What if life could originate in a completely different way? What if it exists neither in water, nor on land, but floats within the cloud layers of a gas giant? This idea sounds like science fiction, but as early as 1976, Carl Sagan and astrophysicist Edwin Salpeter seriously discussed such a possibility. Their point was that, while the core of a gas giant is hellish, its upper atmosphere might contain relatively temperate zones where life could potentially emerge. So, what would these cloud dwellers look like? To visualize this, let's set our destination for a gas giant located 1,347 light-years from Earth, Coro 9b. Coro 9b might be a candidate home for such life, and it could completely your intuition about what life means. The of a gas giant is indeed harsh. Hypervelocity storms, extreme temperatures, giant vortices, intense radiation, all standard fare. But if you ascend to higher altitudes, conditions begin to change. In the upper atmosphere, winds are less destructive, and temperature and pressure are much lower than at depth. According to their reasoning, in these less hellish layers, life could potentially exist. They further speculated that, if a gas giant has existed for billions of years, and its atmosphere has long been rich with complex organic molecules, life might have had sufficient time to evolve into aerial beings. They would spend their entire lives floating in the clouds, never touching the planet's surface, perhaps even unaware that solid ground exists below. Coro 9b is used as an example, because its conditions appear sufficiently similar. It's roughly the size of Jupiter but slightly less massive. Temperatures in its cloud layers average between -25°F and 150°F, -32°C to 66°C. Within that range, complex biochemical reactions could theoretically occur. So, in this planet's upper atmosphere, there might truly float colossal creatures. Some might resemble balloons, others more like airships. Their bodies could consist of an extremely thin membrane, filled with a lightweight gas, using buoyancy to maintain a stable altitude. Only at that specific height do pressure and temperature fall within the survivable range. More crucially, this membrane wouldn't just serve for floating. It might also capture starlight as an energy source. You could think of it as a form of photosynthesis, but it might not follow Earth's chemical pathways, instead relying on a stranger, perhaps even more bizarre, cycle. However, the membrane alone isn't enough. Radiation is too intense, especially ultraviolet light, which could be lethal. How could they withstand it? One direct solution is bioluminescence. In other words, their entire surface might glow red, blue, or green, similar to some corals on Earth. They might synthesize special proteins or pigments that first absorb harmful UV radiation and then convert that energy into safer visible light, transforming deadly radiation into a harmless glow. This isn't mere decoration, it's a defense mechanism. Beneath their bodies, there likely exists a more critical structure, a core chamber. This would house sensory organs, information processing systems, and mechanisms for absorbing nutrients from the surrounding atmosphere. In essence, the upper membrane handles staying at the right altitude and capturing energy, while this lower core handles thinking, sensing, nourishment, and maintaining bodily functions. Thus, they wouldn't be mere drifting capsules, but complete aerial life systems. Regarding size, these life forms could be immense. Sagan once theorized that the largest individuals could be a full mile wide. If we push thee further, in a gas giant's environment, they could grow to scales almost unimaginable to humans. Picture this, a semi-transparent membrane, emanating a soft blue glow, drifting smoothly through the cloud layers, like a jellyfish in the sea, but its size rivaling Mount Everest. Even its core chamber, its operational center, might alone be as large as the Empire State Building. This admittedly sounds more like science fiction than science, but the real point isn't how it seems. It's that such a scenario isn't physically impossible, considering how little we truly know about the universe. This possibility might be less remote than our intuition suggests. After all, Sagan never claimed such life definitely exists. He aimed to emphasize something else. The potential boundaries of life in the cosmos are far wider than our conventional imagination allows. When we think of life, we almost automatically associate it with comfortable environments. However, extreme conditions don't automatically mean a planet is lifeless. Life might exist there, just not as abundantly as on Earth. Sometimes, harsher conditions are even more, because the more severe the environment, the less room for error in evolution, forcing life into ever stranger forms. So, what if the extreme factor isn't temperature or radiation, but gravity? What if everything is crushed under immense pressure? This brings us to LHS 1140b, located 49 light-years from Earth. It's about 1.5 times Earth's diameter, and nearly 6 times Earth's mass, resulting in a surface gravity roughly twice that of Earth's. Don't underestimate that doubling. It's enough to rewrite every aspect of biological design. In such an environment, ecosystems likely wouldn't be very diverse. When organisms endure constant, severe pressure, evolution doesn't encourage risky experimentation, or the pursuit of elegance. Fragile forms don't survive, and agility offers little advantage. All life must be sturdy, robust. Imagine them moving slowly and steadily, with squat, muscular bodies. Their limbs would be short and thick, like pillars supporting their weight. In such a world, swift predators would be almost non-existent, as would light, agile herbivores. More common would be heavy, hard, well-protected forms, specifically adapted to withstand gravitational oppression. Flight would be virtually impossible here, as gravity's pull is too strong. No creature could remain airborne for long. Even jumping would be rare. Life would be pinned to the ground, limited to crawling or creeping, or moving step by step using multiple strong support points, like a mechanical structure resisting constant tension. Life on LHS 1140b might not be large or fast, but incredibly resilient and enduring. The average temperature is around -15 degrees Fahrenheit, -26 degrees Celsius, similar to Earth's polar regions. Cold, but survivable. But what if it were even colder? Say, -110 degrees Fahrenheit, -79 degrees Celsius? That would be like throwing life into an evolutionary meat grinder. Intense gravity, bitter cold, scarce vegetation. Everything pushes organisms to become tougher. These creatures would have even stronger exoskeletons, thicker insulating layers, multiple protective shells, coated with a dense yet elastic substance. This might resemble chitin but be tougher and more resistant to extreme cold. The trade-off, however, is clear. With this cold protection, bodies become bulkier, and movements slower. To survive, they would likely be extremely energy efficient, calculating every move carefully. Their metabolism would be minimal, so low that, during periods of extreme cold, they might enter a state akin to suspended animation. Processes like respiration and metabolism would slow to nearly undetectable levels. To an observer, they would appear motionless, seemingly lifeless. Their pace of life might be slower than Earth's sloths. Sloths on land move at a rate of only a few feet per minute. If you were standing in such a world, you probably wouldn't face any danger. You could even walk slowly among these creatures, observing them as if touring an exhibit. Because your reaction speed and agility would seem superhuman to them, you'd be like a real-life Flash, moving among nearly motionless beings. Paradoxically, more dangerous places might be planets with weaker gravity. When gravity is lower, many restrictions relax, allowing life size and mobility to expand more freely. TRAPPIST-1d is such a candidate, located 41 light-years away. It's believed to possibly have liquid oceans and an atmosphere, but the key factor is its size. It's about 30% smaller than Earth, and 60% less massive, so its surface gravity is only about half of Earth's. On such a small world, certain life forms could emerge, so bizarre you couldn't dream them up in a nightmare. Scientists believe that only rapid, drastic environmental changes, like global cooling, asteroid impacts, or sudden intense species competition, are more likely to trigger major evolutionary leaps. But such turmoil often also gives rise to formidable predators, pushing ecosystems into a state dominated by monsters. Consider the age of dinosaurs, a vast stretch of time, when Earth was populated by strong, fierce creatures. On TRAPPIST-1d, little would prevent a similar world from arising, a world dominated by predators, governed by a single rule: eat or be eaten. Around 1.1 billion years ago, Earth actually hosted a land giant so outrageous it seemed unreal. Sauroposeidon. It stood about 60 feet tall, roughly 18 meters, stretched about 100 feet long, around 30 meters, and weighed over 130,000 pounds, about 60 metric tons. Place it in a modern city, and it could peek into a sixth-story window just by raising its head, an intimidating sight. Yet, ironically, it was a herbivore. So, immense size doesn't automatically equate to ferocity. At least under Earth's gravity, it could sustain itself on plants. But apply this logic to TRAPPIST-1d, and the picture changes. Gravity there is only about half of Earth's, meaning the entire planet encourages life to grow larger. Over billions of years, this release could easily lead to a gigantism snowball effect. The problem is, larger bodies require more food. Paleontologists estimate that a single Sauroposeidon needed to consume about 400 pounds of plant matter daily, roughly 200 kilograms. If body size were pushed even further, resource pressure would become immense, and competition would intensify. At a certain critical point, evolution might shift direction. Originally herbivorous giants might be forced to become predators, not because they suddenly turned malevolent, but because plant matter alone could no longer sustain them. The result, giants begin hunting other organisms, using meat to supplement their energy needs. Give this process hundreds of millions, or even billions, of years, and it could create a world ruled by monstrous-level predators. Theoretically, their height could reach about 160 feet, around 50 meters. In human terms, a 16-story building tall. Weight might approach 400,000 pounds, roughly 200 metric tons. Locomotion might be bipedal, quadrupedal, or involve even more support points. Limbs would be thick as tower columns, jaws wide as buses, fangs taller than a person. But the most chilling aspect isn't just their size, but that there might not be just one. Imagine not encountering a single monster in the wilderness, but the planet teeming with them. Thousands, tens of thousands, all actively hunting. That would be a brutal ecosystem. Predators wouldn't always be the strongest, but they would always be hungry. Stand there, and the sole remaining rule would be, eat or be eaten. Of course, this world couldn't consist solely of predators. It would need a foundational energy source. Thus, herbivores and plants would also be pushed to more extreme scales. Smaller herbivores might specialize in consuming leaves and fruits from colossal trees, and the trees themselves might grow 500 to 650 feet tall, 150 to 200 meters, the equivalent of 60 to 70-story buildings. Furthermore, lower gravity would make flight less energy intensive, so the skies might be crowded with flying creatures, as large as a Boeing 777. Overall, it would resemble Earth's Jurassic period, but more violent, wild, and terrifying. At this point, you might raise a more fundamental question. Haven't we been assuming too much? The monsters we've been imagining, no matter how bizarre, are still extensions of Earth-based logic. What if life doesn't follow this logic at all? What if it originates in a completely different manner? Up to now, all life we've discussed, including ourselves, is fundamentally based on one element: carbon. DNA, proteins, fats, carbohydrates, virtually all life structures rely on it. Carbon's most distinctive feature is its ability to form strong, diverse chemical bonds, and to link with itself into chains. It acts like a set of molecular building blocks, both sturdy and flexible, making it ideal for complex life. But scientists have proposed another possibility. Life in some regions of the cosmos might follow a completely different path, not using carbon as its foundation, but another element. This involves a more fundamental concept: autocatalysis. This means a chemical reaction promotes its own recurrence, leading to accelerated growth and increasing complexity. Most autocatalysis on Earth relies on carbon-based systems, but researchers at the University of Wisconsin-Madison reviewed extensive literature, identifying 7,270 similar reactions, many of which don't require carbon, such as those involving silicon. Silicon is chemically a cousin of carbon, also capable of forming complex chain structures. So, theoretically, it could indeed support an alternative life system. In other words, silicon-based life might exist in the universe, not flesh and blood, but life constructed from different materials and chemical rules. Where might such life emerge? One speculative candidate is Kepler 62f, about 1,200 light-years away. It's about 40% larger than Earth, possibly with an atmosphere, and even oceans. If its surface experiences long-term high temperature and pressure, silicon-based life could potentially develop. Imagine their appearance, nothing like animals. Their bodies wouldn't be flesh but composed of hard silicate compounds, possibly covered in smooth or sharply faceted crystalline shells. Some might have numerous limbs, others no fixed form at all. Some might be massive like boulders, others more flexible, sliding across the surface, or moving by tumbling. Their life processes would also feel alien. They might not breathe oxygen, but instead utilize metals in chemical reactions to perform energy exchange akin to respiration. They wouldn't eat but slowly absorb minerals from soil and rock. As for reproduction, it might be a hybrid between crystal growth and fission, triggered by heat or stellar radiation. Or, more extremely, they might grow new individuals directly from their own bodies or surrounding material, like sprouting a new crystal. The more unsettling thought, you might not even recognize them as alive. Their movements could be so slow as to be imperceptible to humans. What you see might be just a rock, a pile of boulders, or a strange structure, yet they are living, existing on a timescale, completely incompatible with our own. You might think of science fiction parallels, like the silicon-based life in Star Trek that moves underground using acid. But real scientific speculation is even less constrained. Silicon-based life could also be more flexible and aggressive. They could grow to human height, resembling a hybrid of an insect and a crystalline statue, with sharp edges and semi-transparent armor encasing their bodies. This raises an even more. Without DNA, how is genetic information, form, memory, and development encoded? Scientists propose one possibility. In this alien biology, the role of genetic code might be played by complex crystal matrices. Information wouldn't be written in molecular sequences, but in structural patterns within the crystal, like bond density, atomic charge distribution, or arrangement textures. Thus, replication would become a self-organization process. Given sufficient energy and the right elements, an individual could grow another with identical geometric features. Mutation would also occur differently, through changes in temperature or pressure, or the introduction of environmental impurities, causing irregularities in crystal growth. Natural selection would also shift, favoring structures that are more stable, more resistant to damage, and easier to replicate accurately. So, you see, we cannot accurately imagine what alien life truly looks like. We don't even know if it exists. But the deeper you speculate, the more you realize one thing. Life might not be a single form, but a category of outcomes under certain rules. As long as the rules allow, it can assume shapes we've never seen before. Astrophysicist Neil deGrasse Tyson tells a rather pointed joke. If an alien were as large as the solar system, that wouldn't be good news, because even if signals traveled at light speed within it, a simple command like scratch your head could take hours to travel from one end to the other. Hearing this, you understand, life can't be arbitrarily large, or arbitrarily small. Complexity imposes scale limits, but crucially, this limitation doesn't make the universe boring. It merely tells you life's stage has boundaries, yet within those boundaries, space remains vast. You can perfectly imagine various forms of life, some similar to us, others so far ahead in development they've left us behind. So the question becomes, could it be that right now, in some corner of the universe, an intelligent life form not only exists, but is running a civilization we cannot comprehend? For example, using entire planetary systems as tools, deploying them at will, or even treating whole star systems as resource depots and engines, dismantling and modifying them freely. Why haven't we seen them yet? Perhaps not because they aren't there, but because we haven't been searching for the right clues. Think about it. Our most traditional search method involves monitoring for radio signals, waiting for a hello. But what if others have moved beyond that? Then the universe would naturally seem quiet to our ears. So, some scientists are now shifting their approach. Instead of waiting for messages, they look for signs of activity. The most classic example is the Dyson structure, because any large-scale energy use generates waste heat, leaving anomalies that are difficult to conceal completely. This is where Project Hephaestus comes in. Its mission is straightforward: to specifically search for candidate targets that resemble Dyson spheres or swarms. Recently, they analyzed photometric data on millions of stars, applied complex filtering, and identified 7 stars within the Milky Way with abnormally strong infrared radiation. So strong it's difficult to explain with known natural mechanisms. However, this alone isn't conclusive. Infrared anomalies could also be caused by dust, debris, or other natural factors. Their next step is optical spectroscopic observation to examine the details more closely. Whether they are signs of Dyson structures is something no one can yet guarantee, but you can at least discern one thing: we are beginning to search for civilizations with an engineering perspective. This leads to an even larger question. Even if an alien civilization truly exists, could it really build a Dyson sphere around a star? How would it build it? How advanced would it need to be? The scientific community commonly uses a scale to measure a civilization's technological level, the Kardashev scale, proposed in 1964 by Soviet astronomer Nikolai Kardashev. It's not a framework for science fiction but a serious one. The core idea is simple. The scale of energy you can harness determines your level. And human technology is genuinely accelerating, especially in recent years. The pace of AI advancement is staggering. Many have a sense that we might be standing before a technological inflection point. In this context, the Kardashev scale acts like a roadmap. It doesn't guarantee we'll reach the destination, but it shows you the steps you'll encounter along the way. Many scientists now add a Type 0 civilization to describe our current actual situation. To put it bluntly, we are still firmly bound to Earth. Our energy relies on finite resources. We still burn fossil fuels. Wind and solar are just beginning to expand. Nuclear energy has only just begun to tap its potential. Looking at this spread, we can hardly be considered an advanced civilization. Thus, we are fragile. Planetary scale disasters, climate change, resource depletion, anyone could hold us back. Our operational radius is also very limited. Speaking realistically, the farthest we've truly reached is the moon. Probes have visited other planets, true, but that's more like reaching out to touch them, far from establishing a foothold. But don't therefore think we have no chance, because the slope of technological growth is steepening, indicating humanity still has vast untapped potential. If controlled nuclear fusion were actually achieved, our energy system could be completely rewritten. Simultaneously, even more ambitious plans are being considered, like space elevators and Dyson structures. You'll find that the leap from Type 0 to Type 1 might be the most critical jump, because this step isn't just a technological upgrade, it's more like a species-level transition. It requires us to suppress tribal instincts, learn to cooperate as a unified whole, and manage Earth as a single, sustainable system. Fail this hurdle, and even the most powerful technology could be used to destroy ourselves. Once we cross into a Type 1 civilization, the tone starts to feel like science fiction. The hallmark of a Type 1 civilization is mastering its home planet, capable of utilizing and controlling all available planetary energy. Imagine, we could influence weather, neutralize hurricanes before they form, direct rainfall to drought-stricken areas. Deserts would be covered with solar arrays, mountain ranges transformed into wind corridors, complemented by a global fusion network, delivering clean, nearly limitless energy to every corner. Moreover, a Type 1 civilization isn't just about ample energy. It likely achieves global-scale collaboration and governance. Resource wars would become history, replaced by cooperation to advance science and exploration. Artificial intelligence would be deeply integrated into daily life. Nanotechnology would reshape manufacturing and medicine, and genuine space colonization would begin to materialize. Even as a Type 1 civilization, our sphere of activity would largely remain within the solar system. The vast distances between stars would still be a hard barrier. However, for a Type 1 civilization, this is more like a door to eventually dismantle, rather than an insurmountable wall. If Type 1 is about mastering a planet, Type 2 extends that mastery to an entire stellar system. A Type 2 civilization can harness the total energy output of its parent star. Dyson structures are the classic imagination for this level. A solid shell is most likely unrealistic, but a Dyson swarm seems a more feasible path. Using a vast array of structures to surround the star and collect energy, or constructing a ring structure, could achieve similar effects. Once in possession of a star's energy, a Type 2 civilization could accomplish feats that would seem godlike to us. They might move planets, build planet-scale artificial habitats to escape their star's eventual death, hosting trillions of lives. Aging and disease might no longer be inevitable for them. Consciousness might be transferred to artificial substrates, and computing power would be immense. They might even construct simulated worlds indistinguishable from reality. At that stage, the boundary between physical and virtual would blur, and the civilization's mode of existence would be utterly transformed. Yet even as a Type 2 civilization, they would likely still revolve around their own stellar system, because while interstellar travel may be feasible, crossing between galaxies is another level of difficulty. The distances between galaxies are truly capable of stretching any plan to the point of despair. But conversely, here's a sobering thought. A species already capable of fully harnessing a star's energy might see distance as a problem of time, not a matter of survival. For such a civilization, no challenge is permanently insurmountable. It's merely a question of whether they're willing to pay the cost. Now we must pull thee back a bit further, because the next level truly begins to enter cosmic scales. A Type 3 civilization is no longer about controlling a single stellar system. It sets its sights on an entire galaxy. It aims to harness the galaxy's total energy budget. This is so far removed from us that it's almost impossible to visualize. You can only grasp one fact: if a Type 3 civilization exists, it has likely already utilized millions, even billions, of stellar systems. They have either mastered faster than light travel, or found ways to circumvent the lightspeed limit, such as wormholes, or other methods we aren't yet qualified to to understand. At this level, the concept of distance essentially becomes irrelevant. Energy scales also transform completely. The energy at their disposal is no longer planetary, nor stellar, but truly astronomical. They might extract energy from the supermassive black hole at the galaxy's center, or tap energy from spacetime itself, or even utilize extra dimensions we are unaware of to access even more exotic energy channels. Once you allow for such energy levels, many things become truly frightening. A Type 3 civilization could reshape galactic structure according to its will. It might move stars, arranging them like building blocks. It might undertake galaxy-scale mega-engineering, constructing structures as large as solar systems or even larger. You think our solar system is immense, right? To a Type 3 civilization, it might be just a component. Their own form would likely be nothing like the biological organisms we know. They might exist as pure energy, or as vast artificial intelligence networks, or perhaps in a form we cannot even conceive. More extreme, their consciousness might span the entire galaxy, transforming the galaxy into a giant living superorganism, not as a metaphor, but literally using the galaxy as its body. Thus, for a Type 3 civilization, manipulating matter and energy might be routine. They could ignite stars or extinguish them, create or destroy. Within their sphere of control, they might attempt to delay heat death, extending the lifespan of their world. It sounds like mythology, but at this energy level, such endeavors are merely engineering problems. Yet, even more, some theorists continue to push the scale upward, beyond the original 3 types. Kardashev's initial scale only went to Type 3, but later theorists, unsatisfied, added more levels. A Type 4 civilization would extend its influence beyond a single galaxy, possibly controlling entire galaxy clusters, or large portions of the observable universe. At this scale, if dark matter and dark energy could be manipulated, they would transition from mysterious terms to tools. A more extreme speculation is that a Type 4 civilization might even create new universes, perhaps by inducing local inflation, or engineering reality from a more fundamental level. They might act like cosmic gardeners, seeding life, or like shepherds, guiding younger civilizations upward, helping them climb to higher levels. Some have even proposed a Type 5 civilization, one that masters all possible universes and dimensions. At this point, any attempt at description becomes, as from any perspective it would appear nearly omnipotent, omniscient, virtually equivalent to what we understand as a god. But we, standing on Earth, as a Type 0 civilization, might easily dismiss this as. Yet, let's not forget that just over a century ago, human moon landings were also considered pure science fiction. Many so-called impossibilities merely reflect our limitations at the time. Alright, let's rein in our imagination for a moment and return to a more concrete question. What level of civilization is actually required to build a Dyson sphere? Within this framework, a civilization capable of constructing a Dyson sphere is typically classified as Type 2, as it requires harnessing the total energy output of a parent star. Of course, for incomplete structures like Dyson swarms, it's theoretically possible that a very advanced Type 1 civilization might approach the threshold, but to achieve a truly complete form, it likely requires capabilities far beyond our current stage. So, how immense is a Dyson sphere exactly? First, you need to grasp the scale. The sun's diameter is approximately 864,000 miles, about 1.39 million kilometers. You could fit about 1.3 million Earths inside the sun. But a Dyson sphere's scale isn't about hugging the sun's surface. Its radius would need to be at least 1 astronomical unit. The distance from Earth to the sun, about 93 million miles, 150 million kilometers. Hearing this distance, you realize this isn't just a shell. It's an engineering project enclosing a vast volume of space. Consequently, its inner surface area reaches a staggering magnitude, approximately 5.5 billion times the surface area of Earth. In other words, you're not constructing a building. You're creating a living space or energy structure billions of times larger than Earth's entire surface. Consider this, even building just 1% of it is on a scale human civilization dares not contemplate. Therefore, to begin construction, the first step isn't drafting blueprints. It's sourcing the materials. Earth alone is insufficient. Dismantling Earth wouldn't be enough. Materials must come from several nearby planets, even requiring mining asteroids and comets. Mercury is often cited because of its proximity to the Sun, and orbital and energy conditions making it suitable as a raw material source. Essentially, treat the solar system as a quarry. What's a more realistic starting method? Not building a sphere all at once, but starting with a Dyson swarm, ideally deployed by self-replicating robots. This idea is frequently discussed, because logically it seems the most scalable path. First, build a batch of robots powered by solar energy. They begin by constructing collectors and energy transmission devices. The more energy they collect, the more work they can perform. They then build more robots, and the new robots build more collectors. This creates not linear but exponential growth in scale. As for how long it would take to progress from a Dyson swarm to a complete structure, frankly, no one can provide a reliable figure, as it depends on too many capabilities we don't yet possess. But we can make a logically sound range estimate. Pushing ahead with current technological might take millions of years, but if you truly have a highly advanced self-replication system, the process could theoretically be compressed to a few hundred or thousand years. The key difference lies in replication speed and automation level. But don't assume that achieving scale means the job is done. The real troubles often begin at this stage. The first major challenge is gravitational stability. Keeping a megastructure stably orbiting the sun at the correct distance demands engineering precision of an unimaginable order. The second major challenge is heat dissipation. The sun's energy output is colossal. The more you capture, the more waste heat you must manage, or the structure itself will melt from the thermal load. Addressing this requires new materials stronger and lighter than any we know, coupled with extraordinary thermal management systems. And the problems certainly don't stop at these two. The precision required during construction itself far exceeds our current industrial capabilities. But if this is the work of a Type 3 cosmic architect, these are likely surmountable. For them, these aren't impossibilities, just items on an engineering checklist. That brings the question back to us. Do you think humanity could ever reach this point in the future? Not tomorrow, but at the far end of a sufficiently long timeline, might we actually undertake such cosmic scale engineering? Incidentally, even if we do discover stars whose behavior somewhat resembles Dyson structures, we still cannot draw conclusions now, because anomalies do not equate to artificiality. They could also be dust clouds, debris clouds, or other natural mechanisms at play. For now, all we can say is, we don't know yet. We must await more observations and more complete data. Moreover, you'll notice a rather disheartening pattern. We have discovered many strange celestial objects, a host of counterintuitive phenomena, yet to date, the count of extraterrestrial intelligence remains zero. Therefore, we will likely continue repeating this, constantly discovering oddities, constantly ruling out natural explanations, and constantly acknowledging we're just short of that final piece of evidence. For humanity to truly climb to a sufficiently advanced level would require at least another 100,000 years, if we are fortunate, and avoid self-destruction. It might take 1,000,000 years to even approach the of a Type 3 civilization. But the question is, do such civilizations truly exist? If they do, there should not be small. Technological activities of that magnitude, on a cosmic scale, should be very difficult to conceal. Yet, we have been looking up for decades, and have caught almost nothing. This is quite perplexing. Examining the data makes it even more so. According to NASA statistics, over the past 2 decades, we have confirmed approximately 4,000 exoplanets. But the number of stars in the galaxy is overwhelming, and most likely, each star has planets. So, why haven't we found any convincing signs yet? This is known as the Fermi paradox. Its core can be summed up in one sentence: the universe is so old, and so vast, we shouldn't be alone. Yet, we seem to be shouting into a void. Another possibility is even more disheartening. Perhaps it's not that they don't exist, but that we are searching in the wrong direction. Our current search for extraterrestrial intelligence, SETI, often focuses on fixed frequencies like radio and television bands, but these signals are more like byproducts of a Type 0 civilization. Essentially, noise accidentally leaked out. Traveling through space, they get degraded and scattered by various interferences, their information becoming increasingly fragmented. So, how would an advanced civilization transmit signals? A more probable approach would be to disperse information across a wider bandwidth, or even across many bands, to preserve information integrity. But here's a Type 0 civilization accustomed to listening on, even if it did encounter such a signal, might be unable to decode it. What you'd hear wouldn't be a sentence, but noise-like fragments. Thus, a very strange scenario could emerge. The Milky Way might not be quiet, but to us, it sounds quiet, because we don't understand it. Another is searching at the galactic level. Researchers from the National Astronomical Observatories of China proposed an approach. A professor and her team scanned a large region of the sky, identifying 21 galaxies, seeking unusual radio signals to exhaust or traces of technological activity. They found 2 of these galaxies to be peculiar, with enhanced infrared emission. That was difficult to explain through natural mechanisms. Some can't help but think big. Could it be vast collections of Dyson structures, or even entire galaxies deeply utilized by one or more civilizations? But caution is necessary here. To solidify this, the first step is still to determine what is causing the infrared enhancement. We must exhaustively all natural explanations. The Fermi paradox also has a more. Perhaps they are deliberately hiding. The universe is vast, our failure to find them doesn't mean they aren't there. We are accustomed to searching for technological civilizations via infrared waste heat, because using energy inevitably produces waste heat, which is hard to conceal. But what if a superintelligent civilization is not only technologically powerful, but has specifically studied how to mimic natural phenomena? Then we might have been searching for the wrong targets all along. We assume we should look for bright anomalies, when the real target might be something designed to look normal. Some advocate for a change in perspective. Instead of always looking for where something extra exists, try looking for where something is missing, because a rather is that. If a Type 3 civilization truly exists, it would harvest almost all usable energy in its galaxy, potentially leaving behind a kind of void. Indeed, vast cosmic voids exist, and in the past, some have pointed to giant voids as potential signatures of intelligent life. But this theory was later. Such as reality, many avenues eventually hit a wall. Scientists haven't given up, but they must admit the road is indeed tough. This leads to another question. Could it be that we are looking at the wrong time? Computer simulations suggest intelligent life might have been more abundant 4 billion years ago. Sounds right, but from another angle, it's not so far-fetched. Earth already had primitive life about 3.5 billion years ago. So, for intelligent life elsewhere in the to have emerged around a similar or earlier time is not entirely impossible. If that happened, they might have long since departed or transformed, leaving us with nothing to see. This sharpens the question. Should we, to our curiosity, search relentlessly, even if it might bring risk? We all share a common ancestor, yet we cannot even suppress hostility among ourselves. So why assume a super-advanced civilization would care more about our survival? Today, we worry about Earth's resources running out. A Type 2 civilization would worry about stellar death. A Type 3 civilization might worry about escaping the universe's ultimate fate. And if we look at broader interpretations of the Kardashev scale, Type 4 and V civilizations might even treat these issues as solvable engineering problems. More extreme speculations even suggest they could theoretically create new universes. A physicist once gave an estimate. To create a baby universe in a laboratory would require energy corresponding to a temperature of about 10 quadrillion degrees. It sounds mythical, but on the scale of such a civilization, it might not even approach it. A Type 4 civilization is almost impossible to truly achieve. But if it were achieved, the implication is direct. You would truly become a creator. And let's not forget, we ourselves are evolving rapidly. Even today, things like microspacecraft are almost within reach. Some are seriously discussing using laser propulsion for extend the timeline further, and a possibility emerges that sends a chill down the spine. Have we already been visited in the past, without our noticing? The probability of us detecting them is almost zero. Even now, we might be under observation, waiting for us to cross the line that makes us worthy of dialogue. Or perhaps they are indeed on their way, but traveling from another galaxy on the opposite side of the universe could take tens of thousands of years. But even if we never find anyone, it isn't necessarily a bad thing. We would feel as if abandoned in the cosmos with no one to care for us. But from another perspective, we have the opportunity to lay the foundation for our own future. Perhaps one day, when those super-intelligent beings look back, they will see us as pioneers, like children learning to walk in the dark. We stumbled blindly, yet managed to carve out a path. There is an even more counterintuitive thought. Perhaps alien civilizations are figments of our imagination, or perhaps they do exist. But it's not them, it's us, our future selves, post-human versions of us. Further ahead, the story becomes even more. If the multiverse becomes some form of new reality, Type 5 civilizations might travel between these worlds, tapping into endless energy. For instance, white holes, theoretical opposites of black holes, might become key in some speculations. Simultaneously, higher dimensions would transition from to discussable research subjects. According to some theoretical extensions, a Type 6 civilization would become multidimensional. If humans were to enter a hypothetical fourth spatial dimension, our three-dimensional bodies might be utterly incompatible, unable to even exist. But for descendants who have reached Type 6, physical bodies might long be unnecessary. They might store consciousness as pure energy, and transfer it between dimensions. The real might then be energy alone, which they could perhaps obtain from extreme phenomena within the multiverse. Thinking even bolder, they might even travel back and forth through time, challenging like causality that we consider absolute. Hearing this, you might think we've reached the peak, but theoretically, there's an even more level. A Type 7 civilization would be described as creators of the laws of nature. Matter, energy, space, time, dimensions, even all natural laws could be written by it. We certainly cannot imagine what that would be like. Some even say we could never reach Type 7. It wouldn't be a group of beings. It would be existence itself. Even if it did exist, we likely wouldn't be aware of it. That said, searching for evidence of high-level civilizations is ironically the most difficult. A more practical approach is to first search for lower-level civilizations, as the traces they leave are more akin to what we can comprehend. According to NASA, there might be around 300 million potentially habitable worlds in the Milky Way, but the number we have studied in depth is only about 55. We have looked at too little. That is also a fact. Telescopes like the James Webb are not only monitoring for biosignatures, but also for signs of technological activity. Many astronomers believe that with our current instruments, if a Type 1 civilization existed within the regions we have studied, we would most likely have already observed some anomalies. Their engineering, their travel, their methods of energy use would be difficult to completely conceal. A Type 2 civilization would be even harder to hide. To collect energy, it requires Dyson structures to surround a star. A stable Dyson sphere is built at a distance similar to Earth's from the Sun. The inner surface area it encloses would be approximately 600 million times the surface area of Earth. In other words, the internal usable area would far exceed Earth's entire surface. According to an estimate by Robert Forward, a solid shell structure with a radius of 1 astronomical unit would require about 10 to the power of 27 kilograms of material, roughly equivalent to the mass of Saturn. This estimate is stringent and may not reflect actual construction forms, but it at least conveys the order of magnitude. An engineering project of this scale, if realized, would not go unnoticed. Yet, to date, nothing of this magnitude has been found within the Milky Way. We have had a few false alarms, though. For instance, the SETI Institute once detected a signal from the direction of HD 164595, a star about 92 light-years away. Some speculated that only a Type II civilization's beacon could be that strong, but it was later discovered to be interference from a military satellite in Earth's orbit. Another instance was Fomalhaut b. In 2008, it was considered a planet, but by 2014, it seemed to have vanished. Explanations flew wildly, until it was later confirmed that it wasn't a planet, but a vast cloud of icy debris, likely resulting from an extremely violent collision between two icy asteroids. A rare event, but still a natural explanation. This pushes the question even deeper. If we can misidentify whether something is a planet or not, how would we track the activities of a Type III civilization engaged in galactic-scale engineering? The current conclusion is, Type III civilizations are either, or simply do not exist within our local cosmic neighborhood. Astronomers have used infrared telescopes like WISE to search for them. Such a civilization would emit vast amounts of waste heat, leaving an infrared signature. But so far, there is no clear evidence. Some have proposed, however, that they might be hidden within. The origin of these voids remains not fully understood. Take the Boötes void, for example. It has a diameter of about 330 million light-years, and contains almost no stars or galaxies. According to some, such emptiness might be related to the activities of an advanced civilization. For instance, shrouding galaxies, encasing stars, or even moving stars. It sounds, but it at least reminds us, that our search may need further expansion. So, finally, I'd like to pose the question back to you. Which scenario do you find more believable? That we are truly alone in the universe, or that others are out there, but we cannot see them, understand them, or perhaps we have simply arrived too late? And, the more critical point, if one day we truly confirm that intelligent life exists,